Thanks very much for your time, Crystal. Here we are at 1:30 Eastern Time. Uh, I'd like to introduce my colleagues to one of my colleagues on the National Electrical Code, Crystal Hunter, and she is on several panels. This is Crystal's LinkedIn profile, and I'm hoping, Crystal, that you would tell a little bit about what you do for General Cable, and then what we're going to do today is go through some of the nuts and bolts, what I call the nouns and verbs, down in the weeds. Sometimes we call it the skunk works, we call it the plumbing, where the places in the code where you really need experienced people looking at what's going on between the lines. So Crystal's very good at that, and I'm going to let her tell a little bit about herself, and then we can get onto our agenda. Go ahead, Crystal.
Thanks, Mike. Appreciate you arranging the call today. I am a Director of Field Applications Engineering for General Cable. So I manage a team of field engineers on the West Coast. That's about 50% of my job. The other 50% is participating in codes and standards efforts in North America. So I serve on the National Electrical Code on Code Making Panel 6 and 7, which deals primarily with conductors, ampacities, and also wiring methods on Code Making Panel 7. And then I also serve on the Canadian Electrical Code and quite a few UL standards and other industry codes and standards. So I'm pretty well involved in the North American codes and standards efforts.
She is. She's being modest. She's certainly my go-to person, and I like to identify you as a code writer and a vote getter. It's not a very prosaic term, but it pretty much much like my title, for example. But it's exactly what we want to do. We want to be somebody who can put some original words on paper, and somebody who has data to back up the claim and can persuade a technical committee that this is the right thing to go for the direction the NEC is headed, and to make it stick, and then to drive it into the culture. So this is how innovation occurs on a daily basis in the U.S. economy, and certainly having an expert like Crystal available to show us how it's done and what direction we're going is a great privilege for us. So Crystal has asked that we cut over. I promised you nuts and bolts here, folks, and so we're going to march through a number of specifics for what we understand is going to be the 2017 NEC, and let you have and Crystal's going to give a little bit of background on this, and then I'll cut over to the next section that she'd like to dwell on, and I think we'll be done in about a half an hour. So, Crystal, you've asked me to start here, and I'm going to let you talk from your heart about this one, because I know this one is actually it's rather important to both of us. Go ahead.
Perfect. Thanks, Mike. The first one that we're going to look at is 110.5. And of course, we're in the National Electrical Code. It's a very small change if you look at the words that are added and deleted, but it reflects, I'd say, a major cultural change within our industry. The NEC has allowed and recognized aluminum conductors since the early 1900s, but quite often you find that people in the industry either think that there are great restrictions on its use. Some people don't even realize that the code recognizes and allows aluminum conductors in many of our applications. Of course, if you go to 250.118, you know it's allowed as an equipment grounding conductor. If you go to Article 310, you know it's allowed as a phase conductor or a neutral. But having this recognition, you can see where we've added, or where Code Making Panel 1 has added the words "for aluminum" in the very first sentence. That gives explicit information to the code user that copper and aluminum are our two primary conductive materials that we use within our electrical systems.
If you go back to some of our, we recounted some of the history of this in previous presentations. If I'm not mistaken, this has been around for 50 years. Is that, I mean, Peter Pollock was hammering away at this for, I think, since the middle 60s, was he not?
I talked to Pete last week about this, and he was, I think, a little surprised. He said he's been trying to get this changed for over 30 years. I think he said the first time he tried was about 35 years ago. So he was happy that the change finally got made.
To people outside the code universe, I'm not sure how much of a universe it is. You know, it's difficult to change the NEC, but it's not impossible to change the NEC. So this has significance to our industry because if there was any fears by facility managers that we were doing something that was not permitted in the NEC, that's not true at all. But this particular language here tend to serve the purpose of confusion. If you were to take aluminum out there and read this, it looks like it's still biased toward copper. But
yeah, and Pete Pollock, for those of you who don't know him, he worked for the Aluminum Association for over 30 years. He worked for General Cable for a few years prior to that, and he just retired 2 or 3 years ago. Now he's teaching classes in the Washington, D.C. area. He said he was just talking to the head of an engineering department at one of those universities, and that professor still believed that aluminum was not allowed in the National Electrical Code. So you can see that if you're not a code user, if you're not in this day in and day out, there are still people who have the wrong beliefs out there. This puts it right in the front of the code and makes it clear to people who may not be involved in it from day-to-day activities.
And for our purpose, for the past better part of 100 years, aluminum has been 1/3 the cost of copper. So to some degree, I can't spend forever trying to get my industry to do this. I think this is another nail in the coffin to the confusion about it. Frankly, you and I have other stuff to go after, but to get this one behind us, and for those of our colleagues who actually believed us all along, I have to express my gratitude. I will say that they're still outnumbered by people who say you cannot use aluminum or you should not use aluminum. And I think now that we've got this, we have to say we won this one and onward to other battles.
And from a manufacturer's perspective, we make copper conductors, we make aluminum conductors. We know that they are safe and viable options for the industry, and that's really what you want an installation code to recognize, is every available option that's out there, so that the users can make those decisions on what they would prefer to use.
Mm-hmm. This has more profound implications beyond our just building buildings. I've tried to make the point here. I'll be calling up a article that I wrote that shows how aluminum is an ideal conductor for moving emergency power to places where it wouldn't otherwise. So let me say that again. When the cost of running a power feeder is 1/3 the cost, and that power feeder is an emergency feeder that you don't normally use, that allows you to do certain things. I have so many publications here. I'm on another screen trying to find the thing. But now you can run emergency power several hundred feet. You can combine generators. Do you have anything to add to that, Crystal?
So I think what you're trying to say is that it changes the required justification for installations. You actually, because of the reduced cost, it gives you more flexibility in what you can install and the number of backups that you can install, and just increase the robustness of your system. Am I getting that right? Well,
yeah, I'm going to come to this is a drawing that we produced for the District Energy Association, and the point we try to make here is that when you have a district energy plant like this and you are identified by the authority having jurisdiction that this is your primary source of power and it's sufficiently reliable to be your primary source of power, and you find yourself nested within a utility, and I call it the perimeter utility here, you can use the perimeter utility as your backup source. Now, why is that important? All right, that's one important, because very often the 3 or 4 nines of availability is important for both of these power sources. But more importantly, what I'm driving at here is that here's a generator to a building. This generator could be, the feeders coming out of this generator could go to more buildings farther out. We actually built one of these in the here in Ann Arbor. We have several thousand feet, 1,000 foot, 2,000 foot aluminum feeders. They're not normally used. They're 100 amp feeders, but we were able to consolidate power to 4 buildings with one generator here. One generator is feeding 4 buildings because using aluminum made it much cheaper. In many cases, just getting the wire to the buildings is the prohibitive cost. This generator here is fairly well bid. It's a piece of equipment that's built off-site, and the optimal price has been fairly well discovered. What is not discovered is how much it's going to cost contractors to run feeders to all these places. So our solution has always been, let's just put a generator at every building. So you wouldn't think the fact that aluminum feeders are 1/3 the cost of copper feeders, that would have an effect on greenhouse gases, but it does.
It also reduces your ongoing maintenance and testing, because with generators you have to test them on a schedule. So now instead of having 4 or 5 different generators that you have to maintain and test, you have one.
Yeah. So yeah. There is a condition. You're going to want your control wiring to be adequate. And very often, and there are some restrictions upon how you run your feeder through the building, but suffice to say that the cost of running power now to all these buildings that we showed you on our figure there is now 1/3 the cost. So you can consolidate feeders. You can consolidate feeders to buildings, and so that's one of the unexpected benefits of the price difference of aluminum. So I wanted to bring that dimension in here, because it's not always known, and it is significant in an environment where we're all trying to reduce our greenhouse gases. So
that's very cool.
Okay, so what's your next? Where should we travel to next, Crystal?
110.14d. So just a little bit farther along. And this will be our last one in Article 110. But if you come down to the new D right there. Okay, this is another one that Pete Pollack actually started the ball rolling on this subject. The new 110.14d gives explicit instruction to code users that if you have a termination or a connection that has a stated torque value, then you will use a calibrated torque tool. And now we've talked about this for years, and the contention has always been that 110.3b, which requires that you install equipment in accordance with its listing and labeling, that would require you to use a torque tool in any case. But that's not the way that it has been interpreted in the field. So, you know, as code users, we know that 110.3b is there, right there. Very simple statement. If you've got a piece of equipment, you install it the way it's intended to be installed. But for I'd say the normal electrician out in the field, when they read that language or they know that, they're not thinking about using a torque tool for, say, a set screw connection. So adding this language explicitly into 110.14 makes it very clear that if you have a torque value on a connection, you have to use a calibrated torque tool to make that connection. And Mike, you've seen the testing that I've done and that my colleagues have done over the last few years. We've gone to trade shows and all kinds of different events with electricians and inspectors and some engineers as well. And we did a field study to see how well electricians could terminate a connection without using a torque wrench. And the results were horrible. 1 in 4 got anywhere close, and we gave a wide range. We gave plus or minus 20% of the recommended torque value, and only 1 in 4 could even get within plus or minus 20%. And the surprising thing to the electricians is that most of them were below the recommended torque value. 56% were below the recommended torque value, and 30% of those connections were less than half of the recommended torque value. And I know from working with connector manufacturers and seeing the testing that's been done, if you don't tighten that connection to the recommended torque, it will have a much shorter lifetime than what it's intended to have. So this to me, encouraging the culture of correct installation by using torque tools will decrease failures at connections, will decrease overheated connections, and it will decrease fires over a period of time after this begins to be enforced. And just real quick, there are some jurisdictions that already enforce this using 110.3b, but they're few and far between. So we're collecting case studies from those jurisdictions to find out how they enforce it, to kind of give options to other jurisdictions where this will be a new requirement.
It's fairly dramatic here. How did you get these pictures?
I actually got these from a testing company. They were published on the internet on a website, and I contacted the owner of the testing company, and he gave me permission to put these in the ECNM article that I wrote on torquing terminations.
Yeah, that's what I've got up here, and we put this here, and I know that Alan and Mike Eby at ECNM allow me to do this, but so yeah, we have all that on this. This is called lower cost here. I'm not part of our website. So, okay, let's see.
And it's really important to facility owners. That's the one thing that I think doesn't get seen very often. You know, you hire a contractor, they come in, they make determinations. Hopefully they're using the right tools, but that doesn't always happen. And that affects your reliability and your failure rate down the road. And so this is a way to immediately increase reliability of your electrical system.
Yeah, I mean, they're doing that with airplanes. Any of those of us who used to drop engines from cars were very specific about how we would replace the heads. We all had torque wrenches when we were kids. I've come from the era of people who used to work on car engines. So torquing was very important there, so it was part of the ethic. You want to talk a little bit about this? Because this is another related code win, so to say.
Right. Annex I was actually added in 2011 NEC, and it was added based on some of the data that we collected doing the field studies with electricians and the torque testing that we did. And once again, Pete Pollock was the one who started this. He put in a proposal in the 2011 ROP stage asking that these values be added to the code. Code making panel said no because those values could vary based on manufacturer testing. So we did all the studying, we came back, and code making put in a comment in the 2011 process, and code making panel 1 agreed to add it as an annex. So that if you have old gear that doesn't have its label or a connection where you simply can't get that information, you have an industry standard set of values that you can use to make a connection out in the field. And that's a good thing to point out. You should always follow the torque values that are stated on the connection or the equipment, but if you don't have access to that, you have a reference right in your code book that you can use to make a safe connection.
Yep. Yeah, in places like the U of M Stadium, some of these buildings have tens of thousands. You figure every circuit has 2 ends, and you've got 3 phases, and you've got your ground, and you've got a neutral in there, so it's when you talk about tens of thousands of terminations that could likely fail like this, it's a fairly serious business. So,
yeah.
Okay, let's get ourselves back to Tara. Where are we going to next?
Let's go to 250.120b.
I love Article 250. It's better than Ambien. Let's see, what is it? 250 what?
120.
250, 120.
I don't know. I sat in part of the Code Making Panel 5 meetings, and I found it fascinating. I think grounding and bonding, as much as it can be confusing, it's very intricate if you look at how the system parts interact. So.
Oh yeah,
but I'm a geek, so.
I do get that. What I mean to say is, if it weren't so detailed, I would be bored. I sort of think all this is settled science, and it's always a surprise here that it actually isn't. And for the record, Elliot, I always vote neutral, or I abstain from Elliot Rappaport's proposals to change globally everything from grounding to bonding as a professional courtesy. It usually doesn't go in his direction, but Elliot, we love you, and I never vote against you. I always abstain, even though I can tell the committees will, just for those of you who don't, Elliot Rappaport's kind of like the unimpeachable acts in the grounding and bonding space, one of them, let's put it that way. And so anyway, so with that little diversion, go ahead, tell us what you want to talk about here, Crystal.
Okay, 250.120b. We're talking about equipment grounding conductor installations, and the language that is in B has been there for decades. But I've started to get questions from inspectors and installers over the last decade or so as to what that language actually meant. So there was some confusion out in the field. So I submitted a public input, and I think a couple of other people did as well, trying to clarify this language to tell people what it means about terminations within 18 inches of the earth for aluminum and copper-clad aluminum conductors. And there was a task group on Code Making Panel 5 that really worked this over and came up with the language that's shown on the screen. And basically what the change is intended to do is make explicit allowance for the use of sealed wire connector systems. So for instance, if you had an enclosure underground and you were making a splice of 2 aluminum conductors, there are kits out there that are intended specifically for that. But if you read the literal language of 250.120b, you might interpret it to mean that you were not allowed to make any splice or connection underground. So this language allows that. And the other thing that the language is intended to do is to recognize that terminations or connections made inside a listed enclosure are not limited by the connection requirements or restrictions within 18 inches of the earth. So if you come into a piece of gear, if you come into a transformer, and you make those terminations inside that enclosure or any enclosure that's listed for the location, the inside of that enclosure is intended to be or recognized as being a dry location. So even if you have, some kind of, like if you have an aluminum feeder coming up into the bottom of a piece of gear, you can make those terminations wherever the manufacturer wants you to make them within that piece of gear. You don't have to measure 18 inches from the bottom of the enclosure or the earth. So really, what this is intended to do, this language, it's intended to prevent you from putting open, exposed aluminum terminations within 18 inches of the earth. We have very alkaline soil in the U.S., and it can be detrimental to the protective oxide layer of that aluminum conductor. And so we don't want the splash up. We don't want people putting mulch over those connections. We don't want that kind of thing. But it was never intended to prohibit connections made inside enclosures or connections made with listed watertight connections.
Are there any pictures here that describe that? I'm looking for something and I'm struggling. Is something here? That's not exactly it. Can you see this?
No. If you think there are connections out there that have they have like a splice kit, and then they have like a gel covering that goes over it, but I don't see any on these photos. I probably have to send it to you. I know there are several companies that make them. I think 3M makes several.
Can you give me another couple of search terms and we can look at that?
Go look for 3M gel underground. So see the one that says, maybe the one that says Scotchcast. I can't really tell. Oh, there are several on here that might be, but basically you're going to see a connection, and then it has a cover. And here is a resin joint, low voltage armored cable. That's phone wire.
Would you like me to search on? I'll try one more time.
Okay.
Resin wire. Give me another search term.
Try 3M aluminum underground. Okay, see down there at the bottom, like a little bit, that's one, that's a good splicing kit, the picture you're showing now, and the row below that has one as well.
Right here?
Actually, the row of, see the second one over, actually there are quite a few here, like I think that's one, it has like a shrink wrap but I don't think that's gel. Oh, here you go. See see where the car is?
I'm going to
Go to the one right next to it.
I'm going to give you control of the
Okay.
so you can give us a tour here.
Yeah, it's kind of hard when we're in different rooms going, oh, that one.
Okay, so you should be able to wiggle your mouse around and take us to the right picture.
Come on. It's not clicking on it for some reason. I can see my mouse moving, but I still don't have control.
Let me try. Let me look again here. Crystal, I'm going to give us all control and try that.
Okay.
Go to the far right. Go to the far right. Can you do that there? No? Okay.
No,
Well, we may not be able to do that in this mode, so regardless, I think we get your point.
If you see where you see the car, and then there's some connections, and then there's a tape roll that says something sewer, the picture in between where it says Figure 1, Figure 2, and Figure 3 is a good example of an underground splice.
So where you can see can you see my mouse running right now?
No, but you see where the car is, the back of the car? It says, like, the license plate has come on or something like that.
So we really are looking at a different screen here.
Okay.
All right, so let's see. All right, so we did our due diligence here to let everybody see what we're talking about. Okay.
Basically, you just look for kits that are, they're listed for the purpose, and they'll tell you, the manufacturer of the splice kit will tell you what it's intended for underground splice, for direct burial, for whatever. So.
Okay. Where are we going next, Crystal?
Well, if you've got a couple more minutes, let's go look at 310.15 B3C.
Okay, so I'm going to take control. It looks like you are, whether you know it or not, you actually are.
Yeah, it'll let me click on the screen, but it won't let me click on the photos within the page. I don't know why.
Okay, well, so then let's I can't do that now. So 310 what?
310.15 B3C.
So while I'm doing that, I didn't embarrass the fact. 315, you say?
310.15.
Okay, dot 15. Dot 15 here.
B3C. And I can't see your Terra screen anymore, so I don't know if I've got a problem on my end or...
Is that right? Okay, so here's what happens. So let me go back to my spot here. I'm gonna. Oops, we just lost it. I think you should be able to see it again, right?
I can, yes.
Okay, good. So, all right. So, what you got?
So move up just a little bit so that we can see all of the green area. That's good right there.
I'm going to unzoom this because I had it zoomed a bit.
Okay.
Okay.
So we can come down a little bit. Let's see, no, sorry, here we go, right here. So if we look at C, right in the middle of the screen, right there. So what happened is there was a lot of controversy about the temperature adders for rooftop installations in the 2011 and 2014 code cycles. So Code Making Panel 6 requested an independent task group appointed by the correlating committee to evaluate the information that had been submitted before and come up with a recommendation for the code making panel, which they did. They enlisted the help of heat transfer specialists, professors at multiple universities. They included representatives from labor, from testing labs, engineering representatives, and the recommendation they came up with is that we actually don't need all of the rooftop adders that we have in 310.15 B3C. See if you look at the table where it says distance above roof to bottom of raceway or cable, what they found is that the only time you might need an adder is if the wiring method is in direct contact with the roof. So typically if you put a conduit system on a roof, you're going to use some kind of spacers. It'll be either on blocks, on either pieces of wood or manufactured supports from different manufacturers. So typically there's always going to be some space between the roof surface and the wiring method. And so the correlating committee recommended that we delete the table, and that the only time we have an adder is if the wiring method is in direct contact with the rooftop. The task group did not address the exception, but the code making panel decided to keep the exception and still limit it to XHHW-2. So it's the result of many, many years of discussion and testing, and it was accepted at the meeting. We'll see if it gets accepted in the balloting phase, because there was still some question whether there were enough votes to accept the revisions. But the panel did accept the correlating committee task group's recommendations to delete the table.
Okay, that's a big deal.
Yeah.
Now, where often do we see this? Are we seeing this mostly in runs that are run along a roof?
Yeah, this would only be for installations on a rooftop. And, most times I think people try to keep their installations off the roof, just for the fact that, you usually have to do some kind of maintenance or replacement of roofing materials. But there are times when you just can't. There was a hospital renovation here a few years ago in Las Vegas, and they really didn't have any other way to route an additional set of feeders than coming from the gear and up over the rooftop. Fortunately, we didn't have these adders in the code, the adopted code at the time, so they weren't impacted by them. But if it had been in effect, they essentially would have had to double the size of those conductors. Mm-hmm. So it makes a big difference to the size of the conductors that are installed, especially in hot areas.
Saying a lot of that's a big deal. Yeah. Okay. All right. So while we're at it, you know that I never fail you, and I hope I don't embarrass. I hope you're not embarrassed by knowing me. I periodically put out a proposal out there that we want to take all these numbers here. Where's my favorite table here? I think it's 315. Right around in here. Those are the correction factors. So we have this table that I guess this is close enough. I think it's 15. It's the one
B16.
Is it 16 now? Yeah. But
you're looking for 310.15 B16. So come up just a little bit. You're on 21. There's 19. A little bit more. There you are. Right there.
Okay. All right. So I never fail to try to get the committees to look. What it apparently looks like is I'm trying to drive 110 amps through a number 2. I'm trying to drive 195 amps through a 3-aught. And I think if it were only if I'm trying to drive 260 amps through a 300, if it were only the copper, if it were only we can do it. It's only a 15% difference, but I think my industry has to hear it from an expert on the other parts of a power delivery system. Are you ready to talk about that, Crystal?
Sure. And I am on Code Making Panel 6, and we did get your proposal to adjust those tables, basically adjust the conductors up one size or one value in ampacity. And what the Code Making Panel decided is that without testing, without some showing that this is still safe, then there's really no way to accept the proposal. And so basically what the Code Making Panel wants to see is testing from independent laboratories or independent sources that shows that this is still going to be safe for all of the installations that we anticipate these conductors being installed in the field. So we have, IEEE 835 has thousands of ampacity tables for covering so many different conditions. We have just a very few ampacity tables in the NEC, and we expect those tables, especially 310.15b16, to cover every conceivable installation. So you have, in this case, we have to prove that that current going through that conductor is not going to damage the insulation, it's not going to create a fire or create a hazard, whether you're putting it in an attic or on the outside of a building or wherever you might install it. So their basic Code Making Panel is basically looking for justification to change the ampacity values for those conductors.
Right, and I often propose concepts that don't have funding yet, so that when I do go in for funding, I'll say I tried this already without funding.
Yeah, you're like, I've already done that. All right.
Right. So in any case, Yeah, I'm often taking my inspiration from the European electrical designers. They're far more, say, they tend to custom engineer their material a lot more. And also, we also have to remember that you always have a default table. You don't have to use this. You can use this, where's our Nair McGrath? Here we go. You can use this. They almost never do. And when a contractor is bidding a job, a smaller job, maybe there's not a lot of difference. Well, actually, in the case of, when you get in the case of say, a 400 amp feeder, I mean, the difference between, if I wanted to drive 420 amps through a 500, there's two parts to the problem. One of the problems is did he calculate this number correctly? I'm working this on many fronts, but my thinking here is we probably could take 15%, 10-15% out of this, which is what generally the difference is. But if I was thinking, you might say something a little bit about what the termination temperatures. We have to coordinate the temperature classes of our terminating equipment and our insulation.
Yeah, we do, and that's a big consideration. This has been that's been a huge topic of discussion in the Canadian electrical code process, and it's always an issue to consider in the NEC. If you look at the way switchboards and panel boards and any of what we call temperature-sensitive equipment is tested, the manufacturers take the conductor size out of the 75 degree C column that matches up to the expected load on a rating of the equipment, and they test it for temperature rise at those terminations. So the larger the conductor, the better the result is. So if you tested a piece of equipment with 4-aught and you got the appropriate temperature rise, but then you only installed a 2-aught, there's a good chance that termination will overheat if that equipment is loaded to the rating that it's been given. So you always have to look at the terminations before you make any changes to the ampacity allowances for conductors.
Yeah, I acknowledge that this may well be as difficult it's an intractable, not intractable, but it's a very difficult infrastructure topic. It would be like saying, well, let's start riding on the left side of the road. You're not going to get, that may not be cost effective given all the other alternatives you have. So I don't doubt that, but I don't want the NEC committees to think that I'm not challenging them a little bit. You got something to talk about?
That's true, and there's always the possibility of going back and challenging the original ampacities. There was a presentation to Code Making Panel 6 from the Correlating Committee Task Group that looked at the rooftop issue, and they went back and found the history of our ampacities, and the numbers we used were actually determined, I think, in the 1940s, and it was based on testing, but also with a healthy factor in there. I think it was there was a professor or an investigator that determined the temperatures that corresponded to the ampacities. The committee that looked at it then took 60% of those values and said, okay, this is what we're going to use, so we have a significant margin of safety.
And I'm not against safety margins. As I try to tell people, I'm not against transformers that are 2 or 3 times oversized. I'm against transformers that are 8 to 12 times oversized, and the NEC permitting that in many cases. So, okay, let's see here. What's next, Crystal?
Yeah, we know we've gone over our half hour.
How much more do you? Tell me what other topics you'd like to cover.
I hadn't really thought of any for this call. Was there anything else that you came up with that you thought was terribly fascinating?
Well, no, you're my cable go-to person, so you've covered all the cable issues, and I think for that reason, that's the topic of this particular clip will be mostly. Go ahead.
On that side, there are two things that might be of note. The first is that on Code Making Panel 7, we accepted proposals to require listing for the cable wiring methods, almost all of them. It wasn't appropriate for gas spacer cable because of the way it's made, but for pretty much every other cable type, we're requiring listing. And most people think that that's already required, but it's not required by the code. Now it will be. The other thing is
where's that now, Crystal?
Let's take a look at let's say 320.6. Let's look at that one. That's a good example.
Yeah, this will be the title 320.6.
It's new, so yeah, just open up like 320 and you'll be able to see it. There you go. 320.6 listing requirement. So type AC cable and associated fittings shall be listed and labeled.
Okay.
I'd say almost all cable that's installed in the U.S. is already listed, so it's not a big change for manufacturers or installers, but this prevents any case where, let's say someone would try to come up with a cable that didn't meet all the requirements of the standard that's existing. So now the code will explicitly require it.
Okay. Hard for me to believe that our inspectors allow anything other than this. How much of a problem was this out there in the field?
I have seen instances where it has been attempted, but I usually work in large jurisdictions. I don't know, and if you think about it, we have thousands and thousands of jurisdictions in the U.S. Some are more rigorous in their inspection than others. So I don't believe that it's a big problem, but this prevents it from becoming a problem.
This is used a lot in kitchens, I think, right? A lot of residential.
AC cable is, yeah, it's primarily for, it was only for branch circuits and feeders. It can't be used for service entrance, and it would be typically for 15 and 20 amp circuits.
Yeah. Okay.
The other small change is the addition of medium voltage cable in some of the hazardous location areas where it looks like it got overlooked. For example, you could use MV cable in...
Are we in 490?
Let's go to... No, we're in 501. Let's go to 501.10.
Oh, yeah.
Wiring methods.
Okay.
And if you just click on that, so
quite a bit here, isn't there?
yeah, you can see that maybe it wasn't in 501. I can't recall now. It may have been in 502 and 503. Let's go to 502. There were two locations where it was added. So let's go to 502.10. And so one thing that got added, if you see in 502.10a5, ITC HL was added in Class 1 Division 1. And it was already allowed in Class 1 Division 1, so it seemed appropriate to put it in Class 2 Division 1. And then if you come down a little bit and look at the Class 2 Division 2 language, you can see in 502.10b6 where MV and TC were added right in the middle of the page, a little above where you're highlighted. And so if medium voltage was allowed in Class 2 Division 1, obviously it should be allowed in Class 2 Division 2 because it's a lower risk area. Mm-hmm. The code making panel also added TC just as a recognition that if you're allowing TCER, you should also be allowing TC, which is tray cable. So minor changes there, and in my opinion, it's more of a cleaning up than anything. Yeah, exactly.
Well, okay, I think the status of wiring, of core wiring method changes to the NEC are fairly well covered here. And we still have, until April? We've got votes coming up here not shortly, but part of what I'm doing, I have that, I don't want to dig up the calendar. Do you know it off the top of your head?
I believe that the due date is April 6th, and then we should see it at the final ballots at the end of April.
Right, yeah. And that's...
And the correlating committee is meeting in the middle of May.
Okay. All right, well, I'm going to get ready for the 3 o'clock presentation to the industry. As you know, that I still hold APA's vote, and every time before we have a balloting session, I like to let them see what's in process. Just like you, I can't see everything right now. You've told about everything you know in your committee. I will be out speaking about the committee that I'm on, and that's about as good as we can do now until the entire first draft report's released after balloting. So, but this gives our industry a chance to have some insight into what we proposed and that you know more about. You're actually on the committees where many of my proposals were presented. By the way, were any of the IEEE 3000 series proposals accepted that you know about?
I believe some were and some were not.
Well, there were 43 of them. So I'd be happy if I get 4 of them. So that means if you got some of them, a lot of it is contingent upon whether the document has actually been released by the IEEE, but I'm glad to hear that.
Yeah. We'll have to see what your percentage was for those.
Right. Yeah, I told my boss I put out 87 proposals. If we get 8.7 approved, I'll be pretty happy. So.
Oh.
Okay. Well, all right. It's always fun to talk to you, especially having a privilege to talk to somebody so knowledgeable. So with that, Crystal, is there anything else? Any final reflections? Anything I can do to help you?
Nope. Thanks for all your help. I appreciate the time and energy you put into this, and you always have fascinating proposals, so please keep sending them in.
That's right. Keeps you awake. He's proposing what? And then like 6 years later, it's code. So, okay.
There you go.
Thank you very much, Crystal. Take care.
Thanks, Mike. Have a great day.
You too.